So segment 4 of chemical reactions and quantities. So up to this point, we've talked about chemical reactions, and then we talked about balancing, excuse me, and then we talked about types of reactions, and we looked at the first 4 types, being combination, decomposition, single replacement, and double replacement. The next type we're going to look at is called oxidation and reduction. So this would be type 5. Now this one's going to look very different than the others because here we're going to be looking at moving electrons. I mentioned earlier, whenever we had transition metals, they would keep their charge from beginning to end, but eventually they would not, and here's where it is. So once we get to oxidation and reduction, those transition metals can actually change charges within the reaction. Now they always have to come in pairs. So oxidation is one half of the reaction, reduction is the other half. All right. Oxidation is the loss of electrons. So one of the metals or one of the nonmetals is going to lose electrons. We know that's probably going to be the metal, right? Metals typically are the ones that get oxidized. And then reduction is going to be gaining those electrons. So the same electrons are being lost by one of the atoms there, and then a different atom is gaining those same electrons. All right, and that's oxidation and reduction. Now, to keep track of oxidation and reduction, what we have to understand are oxidation numbers or oxidation states. When dealing with simple ions, it's really easy because it's simply the charge on the ion, right? So for example, group 1A, we know that entire group is going to make a +1 charge. Well, the oxidation number for all of those are also +1. For group 2A, it's going to be +2. And for group 7A, it's going to be -1. Now, there are some others that have to have some rules. And so oxygen is typically going to be -2. Now, it can be -1 whenever there's a peroxide, but those will be special cases. And so for us, we'll see it in hydrogen peroxide, but typically oxygen is going to be a -2. Hydrogen can be either +1 or it can be -1. You have to look at what it's connected to. If hydrogen is bonded to a nonmetal, then it's going to be +1. But if it's connected to a metal, then it's going to be a -1. All right, so oxidation number then for elements in the elemental state, it's also pretty straightforward. It's simply going to be 0. In other words, if we're looking at atoms of like nitrogen gas where it's N2, the oxidation number is going to be 0. If it's sodium metal just sitting by itself, then it's also going to be 0. P4, again, 0. Any of the diatomics are going to be zeros. All right. So the next thing we wanted to be able to do then is calculate or assign oxidation numbers for complete compounds. And so we'll start with water. Now water we know is H2O. So the first thing we'll do is we'll look at our rules. Do we have any rules for hydrogen and oxygen? And the answer of course is yes. For oxygen, we know that it's a -2 except when it's in a peroxide, and water is not a peroxide. So here oxygen should be -2. Hydrogen, since it's connected to a non-metal, will be +1. All right, so pretty straightforward. All right, now they can get a little more complex. Let's do something like HNO3. Now, I didn't give you any rules for nitrogen, nor did I give you any rules for group 5A. So what we're going to do is we're going to look at the things we do know, and then whatever's left over is going to be the nitrogen. So hydrogen, we now know is going to be a +1 because it's going to be connected to a non-metal. We know that oxygen should be a -2 except when it's in a peroxide. This is not a peroxide, that's nitrate. And so then what about the nitrogen? All right, so again, we'll just have to calculate the nitrogen. So what we're going to do is we're going to take the two pieces that we know. We know that hydrogen is a +1. We know oxygen is a -2. We do have 3 oxygens though. So that's a total of -6. Now, just like charge on a compound, the oxidation numbers have to equal 0 when we sum them up. So now we're going to look at what's left over. If I go for the summation, +1 plus a -6 plus whatever's on the nitrogen has to equal 0. So mathematically then, nitrogen must be a +5. All right? Hopefully that was pretty straightforward and made sense. Again, if you're struggling with making oxidation numbers, come check it out. Come get a hold of me, and we'll go through it some more. Now, what we want to do is be able to apply this to a redox reaction. So once we've assigned an oxidation number to the reactant side, we'll then assign numbers to the product side, and then we're going to look at how those numbers change. So for oxidation, what we're going to see is an increase in the oxidation number. So for instance, we might see iron with a +2 on the reactant side, and then iron with a +3 on the product side. Its oxidation number increased. It lost an electron, and so we would say that it's been oxidized. Now, while that's happening, something else there has to be reduced. So then we would see a decrease in that oxidation number. And typically it's easier for students to see reduction simply because it makes sense. If I add an electron, I'll see the charge reduce. I'll see it go down. Oxidation is like a new word for us. All right, so let's look at a sample reaction. So here we're going to take iron 3 nitrate reacted with zinc, and it's going to produce iron 2 nitrate and zinc nitrate. Now notice it's already balanced for you. These are redox reactions. There's a special way to balance these that we don't cover until we get to 150. So whenever you're dealing with redox reactions, they will already be balanced for you. What you're going to need to be able to do is assign what's been oxidized and what's been reduced. So let's look at how we're going to do that. So there's my reaction. The first thing I'm going to do is figure out what's the charge on iron on the reactant side. Well, I know the nitrates are all -1 and there's 3 of them. So the iron here must be a +3. How about the zinc? Well, here the zinc is elemental, and so it's going to be 0. So far, so good. Now on the product side, what's the new charge of the iron? Well, there's still nitrate with a -1, and there's 2 of them, so that means it's going to be +2. And then how about the zinc? The zinc is no longer elemental, it's now taken on 2 nitrates, which means it also must be +2. All right, so iron has been reduced then, because iron went from +3 in the beginning to +2 in the products. And if it's been reduced, something has to have been oxidized. The zinc went from 0 to a +2, and so the zinc has been oxidized. Now notice in this whole topic we didn't talk about the nitrate. Well, the nitrate was a -1 on the reactant side, and it's also -1s on both of the product side. So what we say is nitrate is simply a spectator ion. It's been a -1 throughout the whole reaction. All right, so that's 5 types of reactions we've looked at. We have one last type, and honestly, we're going to be looking at combustion, which is just a subset of oxidation and reduction. All right, so what is combustion? Well, combustion is whenever we take what's called a hydrocarbon, so a compound that's composed mainly of carbon and hydrogen. There'll sometimes be some oxygen or nitrogen in there. But for us, it's going to be mainly sugars and smaller organics. So it'll be C, H, and O will be the only 3 elements we'll see there. And this is basically, if you've ever heard of a combustion engine, like in your car, that's what we're looking at. We're going to take that organic substance, that hydrocarbon, and we're going to burn it. So we're simply going to combine it with oxygen. And of course, the products then are going to be CO2 and H2O, as long as it's a complete reaction, right? So as long as we have a complete combustion, and the wording here can get a little crazy because we say, oh, complete reaction, but really complete combustion means that the hydrocarbon broke down completely to make CO2 and water. We can also have incomplete combustion, and incomplete combustion will give us carbon monoxide and water. And so we won't be focusing on that. Our focus is going to be on the perfect world where everything is a complete combustion. So all of our examples will be for complete combustion. So here I have C4H10 plus O2. So notice you'll always see plus the O2. So oxygen has to be in here. And here we have a carbon and a hydrogen compound. Even if the numbers change, the reaction is going to be the same, right? If I add a sugar, so here's C6H12O6, so now we have an oxygen in there. Doesn't matter, we're still burning it because there's the plus O2. Or even if the numbers are exactly the same, that won't matter either. So in all of these cases, your products are always going to be CO2 and water. Now, can I write the water first? I can. It's not a big deal, but the order is not going to matter. Typically, I like to write it as CO2 plus H2O though. Again, even though it's a sugar, because we're saying it's going to be complete combustion, we're going to get CO2 plus H2O. Now, if you recall when we talked about balancing, which is what we're going to do next with these reactions, whenever we're doing balancing, we had that doubling trick. A lot of times that doubling trick shows up when we're looking at balancing combustion reactions. So be wary of that. You know, doesn't mean that every single one's going to be a doubling trick, but you want to remember we've put tools in the toolbox and we want to be able to pull them out whenever we need them. All right, so here we go. C4H10O2. I'm going to put a 4 in front of the CO2. Then I'm going to put a 5 in front of the water. At this point, I'm going to balance my oxygens, and I've got 4 times 2 is 8, plus 5 is 13, and there's that stinking doubling trick right off the bat. So I'm going to take that odd 13, I'm going to put it in front of the O2. I'm going to put a 2 in front of the C4H10. I'm going to make it 8 CO2 and cross out the 4. I'm going to make 10 waters and cross out the 5. So there's our first one. All right, for the next one, we're going to put a 5 in front of the CO2. I'm going to put a 6 in front of the water. And now I'm going to do my oxygen. So I have 5 times 2 is 10, plus 6 is 16. So now I can simply put an 8 in front of the O2. So you can see we don't always need to do the doubling trick. We just want to be sure that we're ready to do it. All right. For this third one, there's a little bit of a trick here too. We have C6H12O6. And then we're going to add that. So this is glucose. We're going to simply combust glucose. We're going to burn that sugar. I'm going to start off doing the same thing as normal. So I have 6 carbons here. So I'm going to put a 6 in front of the CO2. And now I have 12 hydrogens. And so I'm going to put a 6 in front of the water. Now I'm going to calculate out the oxygens. We have 6 times 2 is 12. Plus 6 gives me 18. So I have 18 oxygens on the product side. Typically, I would just take a 9 and put it in front of the O2, but don't forget, we have these 6 oxygens over here. So I'm going to take that 18, and I'm simply going to subtract the 6 out. That's going to give me 12, and then I'm going to put 6 in front of the O2 to give me my 12 oxygens over here. We want to subtract out the oxygens on the sugar because I want to avoid putting anything right here. If I put anything in front of the glucose, then it's going to mess up everything on the product side. So be careful of that too. You want to subtract those oxygens out. Now, if I subtract those oxygens out and it becomes an odd number, the doubling trick will still work. So you'll be able to put that number here, whatever that odd number is, double this one, and double this one, and that will work. All right, give you a little pause here for our last one. And here we go. We're going to put an 8 in front of the CO2. I have 8 hydrogens, so I'll put a 4 in front of the water. I have 8 times 2 is going to be 16, plus 4 is 20. And so I'm going to put a 20, excuse me, not 20, I'm going to put a 10 in front of the O2. All right, so those are our 6 types of reactions with balancing. Hopefully you were able to follow along. Don't forget it is a recorded video, so you can always come back and look at it again and again. If you're really struggling with it though, don't spend all of your studying hours looking over the same videos. Be sure to get a hold of me. When you send me an email, if it's a specific slide you're working on or a specific concept, just put in there on the PowerPoints where it is you're struggling. Don't forget I've also posted the plain PowerPoints. You can print those out and you can work from those as well. All right. The next thing we're going to tackle is going to be chemical quantities. So we're going to introduce you to the mole. Let's see. So how do you measure how much? So in other words, if we went into the lab today, are you able to measure mass? And hopefully you're going to say yes. How about volume? And again, you should be able to say yes, right? We've probably used the scale to measure the mass. We've probably used a graduated cylinder to measure volume. And if I asked you to count the pieces in the lab, if I said, hey, go in there and count the chairs, I'm sure you could do that too. You just go 1, 2, 3, 4, right up to about 20. All right, so for mass, we measure that in grams. For volume, we measure that in liters, but we actually use milliliters. It's just a form of liters though, right, on the metric scale. Now when we do counts, what we're actually counting is we go to moles. Now don't be afraid of the mole. The mole is like a large dozen, okay? So if you can count to 12, then you can count to the mole. It just takes a little longer. Now, the mole is defined by the number of carbon atoms in exactly 12 grams of carbon-12. That part's not important. What's important is that you know a mole is 6.02 times 10 to the 23rd particles. So if you get ready to start an assessment involving this chapter, you want to make sure you have that number written down somewhere because you're going to need it. Now, Again, notice that it's particles, so we have to keep in mind what are particles in chemistry. And I don't want you freaking out. It's a big number. It's got a big exponent. I'm going to show you some tricks on how to deal with it. I want you to just treat it like a very large dozen, though. Okay, don't get worried about it. Just say, you know, I have a dozen donuts, then I know that's 12. If I get a dozen roses, then I know that's going to be 12 roses. If I want a mole of donuts, then I'm going to get 6.02 times 10 to the 23rd donuts. Right? That's how that's going to work. So 6.02 times 10 to the 23rd is called Avogadro's number. People have called it avocado's number. I'm okay with that. I'll probably chuckle, but I know what you mean. So you're going to do the best you can with it. All right, so back to those particles. What are representative particles? Well, the smallest pieces of a substance. All right, so what does that? Now we have to reflect all the way back to like segment 4. For a molecular compound, it's going to be a molecule. So in essence, I can take the mole, the 6.02 times 10 to the 23rd, and make that molecules instead of particles. Or I can make it formula units, or I can make it atoms, or even ions. All right, so we're going to take the word particle out and put one of those 3 or 4 substances in. We can actually do a mole of electrons. We'll do that in Chem 150, though. We don't really do that here in 100 or 110. In these basic and general courses, we stick to molecules, atoms, formula units, every once in a while an ion. All right, so what are the types of questions you'll be facing? Well, how many oxygen atoms are in the following? So if I give you a formula, here's calcium carbonate. How many oxygens are in calcium carbonate? And hopefully you are saying 3 and that was too easy. How many oxygens are in aluminum sulfate? Well, aluminum sulfate is Al2SO4 3 times. So that's going to be a multiplier. We're going to take 3 times 4, and that's going to give us 12. There are 12 oxygens in aluminum sulfate. All right, so those nice little warm-ups. Hopefully they weren't too tough. Now I'm going to ask you how many ions are in the following. And now they're going to get a little trickier. How about calcium chloride? How many ions are in the following? So hopefully you said 3, 1 calcium and 2 chlorides. How about sodium hydroxide? This time I hope you didn't say 3 and you said 2, 1 sodium and 1 hydroxide. All right, last one, that aluminum sulfate again. How many ions are in aluminum sulfate? Well, we have 2 aluminums and 3 sulfates, so that's going to be 5 ions. All right, those were warm-ups. Now, the next thing we're going to do is look at how to do these quantities with the mole. So we're going to end this segment at 17 minutes, and when we come back, we're going to tackle quantities in chemistry.